Good day, everyone, and welcome to this microscopy and analysis webinar, which today is about large area high-resolution SEM imaging and is presented by Raith. Hello, this is Julian Heath for Microscopy and Analysis, and I'm here as the moderator of this webinar, in which I'm pleased to introduce and welcome today's presenter, Dr. Jason Sanabia, who is President and CEO at Raith America. In this webinar, Jason will describe the features of the Raith chip scanner and its applications in semiconductor reverse engineering, material science, and life sciences. This technology combines the resolution and flexibility of the SEM with the accuracy, stability, and automation of the electron beam lithography instrument. With high-resolution SEM, several electron detectors, laser interferometer stage positioning, and field of view mapping, the chip scanner produces accurate large-area high-resolution images. Since the position of each pixel is determined by laser interferometry, these images can be 3D stitched with the highest possible accuracy. Before we start, I'd just like to give out some logistical details about this webinar. You should at this time be seeing the introductory slide on your screen. Remember that this is an interactive webinar, and you can make comments or ask questions at any time during the presentation by clicking the Ask a Question button on your screen. The presentation will last for about 50 minutes, and afterwards there will be a short question and answer session. We encourage everyone to submit questions because even if we cannot deal with them today, the presenter will get in touch with you after the event with his answers. This webinar is also being recorded and will be available on demand in a few days' time. So now on to our webinar, which is titled Perfecting Large Area High Resolution SEM Imaging with 3D Stitching. I will now hand you over to our speaker, Jason Sanabia, who will begin the presentation. Jason, welcome.
Thank you very much for the introduction. I am President and CEO of Raith America, and Raith America is a company whose mission is to support Raith instruments in the Americas and also to drive forward new applications of Raith instruments. Today I would like to tell you about a specific application of Raith technology, and that is large area high resolution scanning electron microscopy with 3D stitching capability. So the agenda for today's webinar is as follows. Some in the audience may not be aware of the Raith chip scanner SEM, and so I would like to give an introduction to the Raith chip scanner. Next, I will focus on two specific applications of the Raith chip scanner. The first being semiconductor reverse engineering, which is an application that the chip scanner has been serving over the past 15 years. Next, I would like to talk about a new application. This is the reverse engineering of neuronal circuits, which is commonly known as Connectomics. Finally, I'll provide a summary of the presentation and a brief outlook as to what is to come for the chip scanner in the near future. Raith Company is a leading precision technology provider. We have Raith staff and partners around the world who are supporting Raith instruments. These instruments are often used in nanofabrication and nanoengineering. We have a wide variety of dedicated electron beam lithography and multi-technique electron beam lithography instruments. We also have focused ion beam and scanning electron microscopy instruments. And during today's presentation, I will be focusing exclusively on the chip scanner scanning electron microscope for large area imaging. First, however, I would like to explain the link between the chip scanner and our electron beam lithography instruments. The story begins with Professor Richard Feynman of Caltech, who gave a speech in 1959 entitled "There's Plenty of Room at the Bottom." In this speech, he suggested that it would be possible to write the entire 24 volumes of the Encyclopedia Britannica on the head of a pin. He even suggested methods for achieving this goal, reversing the lenses of the electron microscope, or taking a source of ions and focusing them down to a very small spot. And Richard Feynman offered a prize to the first team who would meet this challenge, $1,000 of his personal money. 25 years later, at Stanford University, Tom Newman and Fabian Pease met this challenge by using electron beam lithography to write the opening page of Dickens's A Tale of Two Cities. These letters were written at a 25 nanometer line width within a 6 micron square, and this met Richard Feynman's challenge. And Richard Feynman mailed a check to Stanford University and left this world a few short years later. Since Richard Feynman's challenge, there have been decades of electron beam lithography advancements. And in fact, Raith is a world leader for electron beam lithography systems, basically reversing the lenses of the electron microscope in order to enable breakthroughs in nanoscale science and engineering. So in Raith's own history, we have decades of advancements in technology for electron beam lithography. Raith's roots start at Cambridge Instruments and also Philips. And in 1966 and the early 70s, the first electron beam lithography systems were offered commercially by Cambridge Instruments and also by Philips. Since then, there have been many decades of advancements in electron beam lithography technology. The instruments have gotten more and more accurate, have achieved higher resolutions, covered larger areas, gotten more automated, gotten more reliable, and have gotten faster. And nowadays, Raith is currently manufacturing models, several different models of electron beam lithography instruments, including the EPBG and Voyager systems that are shown here. So, we can reverse the lenses of an electron beam lithography tool. Now, why would we go back and do that? This electron beam lithography tool is the E-line system from Raith. It's a very popular model. It has an SEM mounted over a laser interferometer stage and patterning technology. And this is a very popular, top-selling electron beam lithography tool. Now, why would we reverse the lenses of an electron beam lithography tool? Lithography, by definition, is the transfer of information into a material. And essentially, we're going to be reversing lithography. And I'll tell you why in a moment. In lithography, a CAD file is read in by the electron beam lithography instrument. The electron beam is patterned into a resist. The resist is developed, and the pattern appears in the resist. And then the pattern is transferred into the substrate below. And lithography, that's just one step that I described. This loop is repeated over and over again, and a device is built up layer by layer. And these layers must be very carefully aligned to one another to properly build up the devices at the nanometer scale. And so that is lithography. If we reverse lithography, what do we have? We have what we call reverse engineering. And this is a very important application that Raith has been serving over the last 15 years. If you have an unknown device and you want to extract a design from that device, this is reverse engineering. And this is collecting information from a material. So an unknown device is deprocessed layer by layer, and each layer is imaged over large areas with a scanning electron microscope to resolve the very small features in these devices. Each layer can span a large area of about 1 centimeter squared. One layer must be very accurately aligned to the next layer in order to properly extract the design from the device. So over the past 15 years, the reverse engineering scanning electron microscopy has been an enabler for applications such as intellectual property infringement, design verification for hardware cybersecurity, and also design obsolescence, design recovery for hardware obsolescence. So, by reversing the lenses of an electron beam lithography tool, we therefore have what we call the chip scanner. And this chip scanner is a scanning electron microscope that can image areas over centimeter squared areas with nanometer resolution. The images can be stitched together with very high accuracy, and the images can be stacked layer by layer to a very high accuracy as well, and we call that 3D stitching. And so the chip scanner has been serving our clients in reverse engineering for the last 15 years. This is the Chip Scanner 100 model. It's an open architecture that can accommodate many different options, including 4 nanomanipulators for in-situ nanoprobing. There are other models of the chip scanner, like the Chip Scanner 150, which is shown here. The Chip Scanner 150 features an environmental enclosure with very tight temperature control, and temperature variation can cause stitching errors. So the Chip Scanner 150 really has the most robust and advanced stitching specifications among our chip scanner instruments. So the chip scanner is, in summary, a high-resolution scanning electron microscope that brings the advantages of decades of advancements in electron beam lithography instrumentation to scanning electron microscopy. It has special advantages over traditional scanning electron microscopes, those advantages being stitching accuracy, automation, and also speed. So let's have a look at the essential ingredients of the chip scanner. I mentioned the automation. Large area imaging takes a lot of time, just like electron beam lithography. And it is required that these instruments reliably run unattended overnight, even over a few days, capturing these images over large areas. The laser interferometer is a critical ingredient to the chip scanner. This is a high precision stage that can measure the sample position down to 1 nanometer. It uses these beams of these laser beams that are incident on a very carefully manufactured mirror. The reflected beams go back and are interfered with a reference beam, and this is a way to measure the plane of the sample with very high accuracy and precision down to 1 nanometer. We also have, the chip scanner has a state-of-the-art scanning electron microscope column that can be varied, and the primary beam can be varied in energy, just like any traditional scanning electron microscope. Also myriad electron detectors like the Everhart-Thornley detector, the post-lens angular selective backscatter detector, and also in-lens secondary and backscatter electron detectors are all possible with the chip scanner. Finally, we have height sensing apparatus. So when you are imaging over large areas, it is important to keep the sample in focus. And this is a common problem for electron beam lithography. So that's why the chip scanner has built-in laser height sensing apparatus. And this allows the chip scanner to keep the sample in focus over large areas. Okay. So having a closer look now at the laser interferometer stage, here we have a 300,000x magnification image video being recorded here that shows a tin on carbon sample. This tin ball is being moved to the right by the user depressing the joystick on the chip scanner. And essentially, what you can see here is very precise and stable motion underneath the field of view of the scanning electron microscope. And anybody who is used to operating scanning electron microscopes always find that when you press the joystick at this magnification, this feature would be lost, completely lost, and would never be found again. But with the laser interferometer stage, this feature is just slowly moved to the right. And this capability allows us to map out the errors in the field of view. And so let me talk about the errors on traditional electron microscopes. Traditional electron microscopes all have fields of view with distortions, and that's signified by these non-square fields of view. These distortions come from imperfections in the electron optics. They come from nonlinearities in the scan electronics. So this is just a commonality among scanning electron microscopes. Also, mechanical stages for scanning electron microscopes are not really any more accurate than a few microns. And therefore, it's not possible to move the stage and stitch together these fields of view. So what ends up happening is, unless you have large enough overlaps, you can end up missing certain areas of the sample. So large overlaps would be required, okay, for imaging with a traditional electron microscope. And software would be required to fix these stitching errors. However, when you're dealing with thousands of images, software becomes untenable for correcting the errors in these images. A powerful desktop computer cannot correct for more than a few thousands or tens of thousands of images. Beyond that, the problem becomes untenable. But more importantly is that software corrections themselves introduce additional errors inside the field of view as the software is trying to match up the edges of these images. And that makes 3D stitching impossible with software corrections. At least impossible according to the accuracy that is demanded by these applications. So, with the chip scanner, we have a calibrated field of view. The laser interferometer stage is used to calibrate the field of view, making it highly, mapping out all of the distortions, measuring and mapping out all of the distortions. And then this accurate field of view can be stepped with a very accurate laser interferometer stage, and these images can be stitched together. Also, the overlaps between the images can be minimized, and this really improves the overall speed of the chip scanner compared to a traditional scanning electron microscope. So, the chip scanner has a few applications that I wish to share with you now. The first being the semiconductor reverse engineering. In reverse engineering, an unknown chip is deprocessed layer by layer, and each layer is imaged. So here we have 9 metal layers and the silicon poly layer of an integrated circuit. And the first 3 layers can be imaged with the optical microscope because they have very low resolution structures. But as soon as you want to look at this specific area of the IC, you need electron microscopy to resolve the structures. And so the chip scanner is used to image large areas of each of these metal layers, metal layer 6, metal layer 5, all the way down to metal layer 1, and the highest resolution is silicon poly. The vertical and horizontal stitching of these layers, the 3D stitching of these layers, has 1 to 2 pixel accuracy over each layer, and each layer has a total of 10 to the 10 pixels. So our client here is able to use the accurate large area imaging with 3D stitching that the chip scanner provides in order to successfully reverse technologies down to the 22 nanometer node. Let's have a look at how the chip scanner captures a large matrix of high resolution images. So here we have a 50 micron field of view with all the corrections, and all of these corrections are applied in real time as the image is captured. These corrections are stored in the scanning electronics hardware, and so whenever we scan an image, all of those corrections are being applied in real time. Next, the laser interferometer moves the sample and an image is captured. And then it moves the sample and an image is captured, and this is just repeated over long time periods to cover large areas of this particular layer. So now we have about 250 by 250 microns of image captured. Let's have a closer look. You can see the green annotations are showing the stitching boundaries between the images, and this is a 10 micron scale bar down here, so you can see very excellent stitching already. You cannot detect any errors in the stitching. Having a closer look, let's take a look at this section over here, and we remove the green annotations, and here you can see actually a stitching boundary. But the stitching boundary is not some error in X or Y. This stitching boundary is actually a variation in signal intensity, which is another dimension of stitching errors that I'll come back to a little bit later. But here you can see really X and Y stitching is almost perfect. Let's have a closer look at this section here. And what we see here is 10 nanometer stitching error. This is a 300 nanometer scale bar here. So we see these images can be stitched together down to 10 nanometers. Furthermore, each of the images are captured at very high resolution. You can really see very high resolution structures here on this layer. The blue annotations are currently showing a 1 micron overlap, but this is far more overlap than what is necessary. We only show this overlap to insinuate, to show that stitching errors is far less than 1 micron. So by reducing these overlaps, speed can be improved for capturing these images over large areas. We had a look at the 2D stitching in the last slide. Now I want to have a look at the 3D stitching. Our partners at Micronet Solutions have created this video using their chip scanner instruments as well as their PIX2Net reverse engineering software to create this video to show the inherent 3D stitching accuracy that is possible with the chip scanner. So, the following video is going to show the images from 3 different layers of integrated circuit, metal layer 2, metal layer 1, and then a poly layer. So first, we see that the PIX2Net software can read in the images from the chip scanner in real time. This allows the user to occasionally monitor the chip scanner's imaging progress. Furthermore, the PIX2Net software is also capable of aligning different layers of scanning electron microscope images. This is a very large area image that stitched together, one layer being overlaid and aligned on top of the other. So here we are panning around metal layer 2, and this is a 50 and now a 20 micron scale bar. There are no stitching errors observable in metal layer 2. And so we're going to slowly zoom in now. We're looking at the poly layer. This shows the high resolution imaging capabilities. And finally, we have metal layer 2 and metal layer 1 being overlaid at a higher resolution, one on top of the other. The diameter of these vias is 150 nanometers. Now watch what happens when we remove metal layer 2, which contains these vias. You see metal layer 1, we removed metal layer 1, and now we see metal layer 2, and we see that the vias from metal layer 1 has disappeared, and what we have remaining is the shadows on metal layer 2. And this really illustrates very excellent alignment, clearly below 100 nanometer 3D stitching capability that is possible with the chip scanner instrument. So now we are showing different views and excellent 3D stitching on different views of poly and metal layer 1, metal layer 2. So here's just the poly layer, very high resolution structures. Okay. Now the PIX2Net reverse engineering software, it can go further and analyze these images and start converting them into CAD. So now we have CAD design file essentially has been extracted from these SEM images, and color-coded features are appearing in CAD for all 3 layers. So this CAD design file can be further analyzed to identify unknown circuitry. And so here the software has identified the Logic 1 library. And we can see that this Logic 1 library actually consists of a few different NOR, NAND, and buffer circuits. Finally, the software can go and extract schematic netlists and schematic diagrams out of these by analyzing the GDS CAD file. And so ultimately we have really a complete reverse engineering workflow, ultimately producing the netlist and even the electrical functional models of integrated circuit. So, okay, next, for this reverse engineering software to be able to properly analyze the images need to be of good quality. And therefore, the chip scanner has a variety of primary electron beam landing energies and also electron detectors. So here we see aluminum traces on a silicon background. And in fact, these detectors and energies are having a hard time showing a high contrast that is required for the software to properly work. But if we switch now to the post-lens angular selective backscatter electron detector, we see that these aluminum lines are appearing with very high contrast over the silicon background. And so it's very important to have a variety of electron detectors and primary landing energies. And as for any traditional scanning electron microscope, the chip scanner does have all of these detectors and primary beam landing energies. Okay. And that point is driven home again by this schematic showing the three different detectors that can be used in the chip scanner. Okay, next, I want to talk about a new application of the chip scanner, and this is the reverse engineering of neuronal circuits, which is more commonly known as connectomics. So the chip scanner can image neuronal tissue, as can any traditional scanning electron microscope. Neurons make up the brain and the spinal cord, and we see several neurons, a bundle of neurons here in this section. The neurons are the fundamental elements of the neuronal circuits. And here we have an image of neuronal tissue that has been stained with osmium tetroxide and also uranyl acetate in order to produce very good myelinated contrast for the myelinated walls here, as well as the neuronal cell ultrastructure can be clearly resolved at very high resolution with this scanning electron microscope. So I would like to tell you now why we would use the chip scanner for imaging neuronal tissue. And so let me please provide some background. In 2013, the United States launched a $12 billion BRAIN initiative. And the BRAIN initiative is to accelerate the development of technologies that will ultimately show how brain cells and complex neural circuits work. The idea is to map the wiring diagram of neuronal circuits in the brain. And the wiring diagram, the schematic diagram of the brain circuit, is what neuroscientists call the connectome. The connectome is completely unknown for humans and most animals. And there is a large effort to explore and understand the connectome and its implications. As for the United States, the European Union has also launched the Human Brain Project, where they, in one sub-program for this brain project, is to use electron and light microscopy to image the structure and determine the function of the human brain. So it's essentially the same goal. And in fact, several countries have launched major new brain research initiatives. Israel, Canada, Australia, New Zealand, Japan, and China have all recently announced major new brain research initiatives. To understand why neuroscientists are on a quest to map the human brain, let me please share with you the story of Anna Bagenholm, who in 1999 fell while skiing in Norway. Anna was trapped under an icy stream for 80 minutes head first, while her friends did all they could to pull her out. It was 80 minutes had gone by until the medical rescue team arrived, and by that point, Anna was clinically deceased. However, the medical team was able to bring Anna back to life, and this is because her body temperature did not go below a certain threshold. I think it was 14 degrees centigrade. And below such a threshold, cellular damage starts to happen. But the body temperature did not get that low, and so the medical team was able to resuscitate Anna, even after 80 minutes of being clinically deceased. Today, Anna lives with all of her memories, all of her skills, emotions, desires, and her senses. These are all generally intact. And it is quite a miracle that a person can be clinically deceased for 80 minutes and then be brought back to life and then have all of these things still intact. Neuroscientists hypothesize that Anna's persona, her entire persona, is stored within the structure of her brain, within the structure, within her connectome. And therefore, neuroscientists are on a quest to answer very fundamental questions. For example, what brain circuitry do we all have in common? What brain circuitry do we all have already present at birth? And what are the associated behaviors? And what are the associated cognitive skills that we have at birth, just based on the structure that we're born with? So let's have a closer look at the neuron. And again, this is all background to explain why the chip scanner is going to be important for neuroscience and connectomics in particular. The neuron spans many length scales. Here we have the cell body. The cell body can be 100 microns in diameter. We also have the dendrites. They can be 1 micron in diameter but span a few hundred microns long. And so here we have quite a range of scales. We would need to resolve dendrites that are 1 micron in diameter, but they're a few hundred microns long, which already exceeds a single field of view for scanning electron microscopy. Looking at other parts, the axon is very interesting. It is also 1 micron in diameter, but it can be 1 meter long, even longer in certain animals like humans. And finally, let's take a closer look at the myelin. The myelin sheath here, there's about 100 sheets of myelin, and there's about a 10 nanometer pitch. So you need to be able to resolve 10 nanometers over scales of 100 microns, a few hundred microns, and perhaps even much longer, up to a meter, in order to really map even a single neuron. And our brains have 80 billion neurons. So this is an immense problem, actually. Interesting about myelin, just that I want to point out, myelin is an electrical insulator, so it's kind of shielding the bioelectrical, the neural signal that's traveling through the axon. And the degeneration of the myelin sheath is a hallmark of several neurological disorders, such as multiple sclerosis. So, the neuron spans many length scales. There are many neurons to map. And furthermore, the neurons are all intertwined and forming synapses with each other in 3 dimensions. And therefore, electron microscopy with 3D stitching is very important for mapping neuronal circuits. And several groups around the world are already off and imaging small sections of neuronal circuits. Here is one sample preparation method where an in situ ultramicrotome is used to slice neuronal tissue right underneath the scanning electron microscope. And between each slice, a new scanning electron microscope image is captured. And the idea is to stitch these over volumes that are over dimensions that are about 1 millimeter or even up to 10 millimeters is what neuroscientists desire for capturing the essential structure of neural circuits. Now, this will not be an approach for mapping the connectome of the entire human brain. Certainly, this is a very slow process, but still, the ability to do this at the scale of 1 millimeter and 10 millimeters is very important already, can show a very important information for neuroscientists. So there are challenges with the electron microscopy, and these challenges are starting to become known in the neuroscience community, as illustrated by this 2015 paper. Here in this figure, you see that large overlaps are being applied and software is being used to try to correct for stitching errors in the traditional electron microscope. Now, this is essentially the same challenges that semiconductor reverse engineers have been faced with over the last 15 years. So neuroscientists and semiconductor reverse engineers essentially have the same problem, and that's reverse engineering of circuitry, and the chip scanner is therefore, with its excellent 3D stitching, the chip scanner can really enable neuroscience in addition to semiconductor reverse engineering. And so together with our partners at the George Washington University, we set out to make a map of a mouse spinal cord using the chip scanner. And so here we used 100 micron fields of view that already had corrections built in, and the laser interferometer stage of the chip scanner, and we stitched together many such images of the mouse spinal cord. So here you see the axon cross sections, these circles. They're myelinized, so you can see, even resolve the myelin sheets in this image. And you can even see some of the stitching boundaries. Again, these are not displacements in X and Y. These stitching boundaries are due to changes in signal intensity, which is another dimension of stitching errors. And signal intensity changes, that can occur quite easily if there's damage happening to the sample or charging. This can change the signal intensity, and therefore it's quite common to find these boundaries of signal intensity in these stitched images. Okay, so zooming out now by a factor of 3. So we have recorded even a larger area of this mouse spinal cord. And finally, we can zoom out by another factor of 2. And here we see that we have, in fact, imaged the entire cross-section of the width of the mouse spinal cord. So it is important here to note that this is the most accurate large area, high-resolution map of neuronal tissue directly acquired by a scanning electron microscope instrument. This image contains about 5 times 10 to the 10 pixels, and each of those pixels have locations that are known to the accuracy afforded by laser interferometry. We therefore believe that the chip scanner has great potential as an enabler for connectomics. So as for semiconductor reverse engineering, it is important to have a variety of electron detectors for imaging of neuronal tissue. And here we show just 3 different images of the same small area of neuronal tissue. Each image shows different information. This is a secondary electron image that shows topographic information. Here's the energy selective backscatter detector in-lens detector that was used to show a very high resolution but slightly noisier image. And finally, here's the post-lens angular selective backscatter detector as well. So a variety of imaging conditions is possible. And this is important because there are a variety of ways of doing sample preparation. It is quite an art quite a lot of effort has gone into properly preparing these samples to fixate these cells with osmium tetroxide and further with urinal acetate and preserve the ultrastructure and the myelin sheets. It is quite an art in itself. So there are a variety of ways of preparing these samples. And so it's important to have flexible instrument detection capabilities. Here's another sectioning sample preparation method. This is the automated tape collecting ultramicrotome method. And this is interesting because the brain sections are continually sliced and collected from the water bath here, and they travel up along this tape, and these tapes are then laid out down onto silicon wafers. And then these wafers go into an electron microscope for imaging. However, the wafers, they're not perfectly flat, and so keeping the sample in focus is certainly a challenge for this method. And so we believe that the chip scanner would be very well suited for this method because it has a height sensing apparatus that is used for keeping the sample in focus over large areas. Okay, so now I would like to summarize today's webinar presentation and also provide an outlook as to the future of the chip scanner. So, the chip scanner has a special role in electron microscopy. By reversing the lenses of an electron beam lithography instrument, large area high resolution scanning electron microscopy can benefit from decades of advancements in electron beam lithography technology. This includes stitching accuracy, automation, and speed. So, the chip scanner has a very unique laser interferometer stage, and this is a critical piece for large area scanning electron microscopy. The laser interferometer stage is used to map out the errors of the field of view, and so all subsequent corrected fields of view with inherent accuracies can be used for imaging and stitching together of these images with a corrected field of view and a very accurate laser interferometer stage is possible. Furthermore, stitching in a third dimension is possible, and this is very important because the challenge gets much greater when you enter the third dimension in stitching. I pointed out that a wide range of electron detectors are available on the chip scanner, just like any traditional scanning electron microscope. The chip scanner has very high stability for beam position and also beam current. It is a thermal field emission scanning electron microscope, so it has very stable beam current. And these stabilities are very important for imaging over long time frames while maintaining accuracy. Each of the images can have a very high resolution, up to 50,000 pixels by 50,000 pixels, and then these images can be stitched together over very large areas. And finally, the chip scanner has active focus control by laser height sensing, and this is very important for keeping the sample in focus without having to employ auto-focusing routines, which can take time and also cause unnecessary sample damage. Now, as far as where the chip scanner is going in the future, I'd like to conclude today's presentation by essentially sharing with you that Raith is making a contribution to this year's Microscopy and Microanalysis Conference in July in Columbus, Ohio. And here we're going to be talking about how we can enhance the throughput and go towards the eliminating of all four dimensions of the stitching errors. Those dimensions include X, Y, Z for 3D, but also the fourth dimension is signal intensity. And here we will be describing some new technologies that will go towards enhancing the throughput and eliminating all or at least minimizing the four dimensions of stitching errors. So this here concludes my webinar today. Thank you for joining, and we look forward to taking your questions.
Thank you, Jason. Hello, this is your moderator, Julian Heath again. So we have a few minutes left in this webinar for our Q&A. So if you'd like to ask Jason something, please submit your question now. So Jason, are you ready for a few questions?
Yes, Julian, thank you.
Okay, now the first one. With chip scanner, how does the depth profiling work? In other words, how do you get to the next layer physically once the information on the previous layer has been obtained?
Okay, the chip scanner itself is a scanning electron microscope only. It is not a deprocessing instrument. So the depth profiling, each layer is deprocessed layer by layer using other equipment, including chemical mechanical polishers, ion etching, and in the case of collecting the images of neuronal tissue, some ultramicrotomes are separately used.
Okay, thank you. The next question, how do you compensate for drift in the scanning EM?
Okay, drift. Yes, when you are collecting images over long time frames, any scanning electron microscope will drift, and the chip scanner is a scanning electron microscope, and it's impossible to build a microscope that doesn't drift. So this is a common problem for electron beam lithography as well, and so we really understand the problem well. And so the chip scanner 152 has an environmental enclosure surrounding the entire instrument, and that maintains a temperature, a very tight temperature tolerance inside the enclosure where the vacuum chamber is, where the electron optics are, and even the scanning electronics. All of this has very tight temperature control, and that really minimizes the room temperature variance that is coming from the environment. Furthermore, there are automated drift compensation routines that are standard for e-beam lithography instruments, and these drift compensation routines are readily available for the electron for chip scanning, for capturing these images over large time, over long times. So if the images are being captured, and if each image takes some time, and you can set the software to go and correct for any drift, let's say after every 10th image or after every 10 minutes. So it's quite variable. Also depending on the sample. The sample can also cause drift by charging as well. There are several tools available to compensate for drift, and then we try to build also a stable system. Finally, the laser interferometer stage is also a very stable stage to begin with. So that, coupled with temperature control, makes it an inherently stable instrument. So.
Yep. Okay, nice answer. Next question. With the high precision stage and a calibrated image, what sort of overlap requirement would you have to consider?
Okay, so the in a few slides prior, we showed quite a large overlap of about 1 micron, but that's completely overkill, if you will. A typical overlap that we start with is, let's say, 100 nanometers, and if we need any more, any less overlap, it depends on the overall imaging conditions. So if there's a lot of sample charging, or if it's if there's any other source of drift that is giving us problems, you might need some more overlap. If the images each take a very long time to capture, like if you're capturing a 50,000 by 50,000 pixel image, that would take a long time, and so you might want additional overlap there, unless you're correcting for drift after each image.
And here's a sort of supplementary question. How long would it take to image and stitch 22 nanometer sample images? Obviously, that's a kind of an open-ended, but can you give us an example of a typical run?
Yeah, so it is open-ended, and it really depends on the overall area that you're trying to cover. I don't have specific numbers for the images, or even the number of images that were captured for that chip. However, the instrument is capable of automatically capturing these images, and so it can run for days in quite a robust way, just continuously capturing these images. But it really depends on the acceptable signal to noise for the application, and a variety of other settings to determine exactly how long it takes to capture each image.
Yep. Okay, thanks, Jason. Next question. What type of SEM was used in the work that you described in your talk, and also what is your definition of high resolution SEM?
Okay, so the SEM is thermal field emission SEM, and the beam diameters are comparable to traditional thermal field emission scanning electron microscopes. So I would say of the order 2 nanometers is like the beam diameters that we're talking about here. So it's definitely high resolution field emission scanning electron microscopy. In addition, there are a variety of voltages, very similar to a traditional scanning electron microscope, also with some of the inherent features that you would expect in terms of doing different scan rate.
So, for example, in the brain mapping project, you're clearly able to resolve the plasma membrane of each neuron, because that's in the order of 7 nanometers or so.
Yes, that's correct. The myelin sheets and the small features, these can be resolved.
Yeah. Another question. So, we talked about drift. How do you maintain focus during these long operations?
Okay, yes. So the larger area that you scan over, the more the sample can get out of focus. Now we have 3 different ways of controlling the focus over large areas. One is using the laser height sensing, where the laser beam is bounced off the sample and its reflection is recorded. And the position is determined there, and that measurement can be done well within the depth of field of the scanning electron microscope. It's also possible to use a simple planar correction, and finally, it's also possible for the chip scanner 152 in situ. It has the ability to level the sample by basically moving up and down the 3 points on which the sample holder is resting.
Okay, one last question. What is the maximum field size that you can acquire? Again, a bit of an open question, I guess.
Yes. This is, I think, our current limit for the chip scanner. It's a 16-bit machine, and so 16 bits corresponds to about 50,000 pixels. And that's why the instrument has the limit of capturing 50,000 pixels by 50,000 pixel images. Now, if you take a 2 nanometer beam diameter and you multiply it by 50,000 pixels by 50,000 pixels, you end up with a 100 micrometer field of view. Now, it is possible to go to larger fields of view if you increase the step size or the size of the pixel. But if you're matching the pixel size to the beam size, then 100 micrometers.
Okay, thank you, Jason. Well, unfortunately, we've now run out of time, so that ends our Q&A. So this time, I'd like to thank everyone for attending today. Also, special thanks to today's speaker, Jason Sanabia, for his excellent presentation. I'd just like to remind you all that today's event has been recorded and will be available for viewing on demand in a few days' time. There will also be a feedback area should you have any further questions or comments you wish to make. An email with this information will be sent to all of today's attendees. The Microscopy and Analysis team are planning more webinars, and we hope that you'll be able to join us again for our next presentation. So that concludes today's event. Many thanks once again for your attendance, and enjoy the rest of your day. Goodbye.